Hello everybody, welcome. I'm sorry I didn't get to this particular example problem, especially since it's something new because it uses what we call Gauss's law. So Gauss's law deals with a concept known as electric flux. So I know if I have some charged object, let's say I just have a positive charge here, that it's going to send out electric field lines in different directions, and they're going to point away from it because it's the direction that a positive test charge would move. So the idea of Gauss's law is, imagine that you put some kind of surface around this and you measure the amount of electric field that goes through that particular area. So you get what's known as electric flux, which is labeled with a Greek letter phi here, and it equals the electric field times the area. Now that's kind of simplistic, and in the notes I kind of left it as fairly simplistic, except then later I added something that technically this would equal the sum of all the electric fields times the cosine of phi times your area. And the idea is, if you look at, let's say, a little section of this particular surface, what we actually do in mathematics is we give areas a direction, and they're always perpendicular to the surface, or in other words, they're a normal. So the area of this would have a direction in this particular case. It would actually be a vector like that, which is kind of weird. And then if my electric field were to come out of this, let's say the electric field was pointed in this direction, let's say there's my electric field, then the phi would be the angle between these two. So here, my wonderful calc people, the true definition of the electric flux is actually your electric field vector dotted with your area vector. So that's why we write it as the electric field times the area, and then times this little cosine, and little phi is actually the angle between those two directions. But the weird one is area actually has a direction, it just happens to be normal to it. And then if you want the electric flux, you actually sum all of those. So you take the sum, or the average of them. So actually you'll often see this written, this is going to get even more complicated for my calc people, as the integral of E dot dA, and so we integrate over the entire area, the surface area. So just kind of getting nice and fun. Now, we don't really need that for this particular problem because the Gaussian surface that was chosen was a sphere, and I know how to find the area of a sphere. The area of a sphere is just 4 pi r squared. So that's going to stay like a constant. We don't have to worry about any kind of integrals down here and stuff like that. The other thing is the object itself is a sphere. So we often pick areas that kind of match with that. So what Gauss's law basically says is that if you actually find the electric flux, which is the sum of all of your electric fields times your areas times the cosine of phi, it would equal the charge enclosed, so the Q enclosed by that Gaussian surface, divided by epsilon 0. So epsilon 0 is a thing called the permittivity of free space. So this is all in my notes. Permittivity, free space. Actually look this up. And it's just a number. So it's just a constant. It's 8.85 times 10 to the negative 12. It does have a unit. It's newtons per coulomb over meter squared or something like that. I don't remember what the unit is off the top of my head, so I apologize. I'm not going to really worry about that to kind of figure this out. So in this particular problem, they say find the magnitude of the electric field at any point outside the sphere and inside the sphere. And they give us the size of the sphere and the charge of the sphere and that type of thing. So here's the easy method to kind of go about this. If I'm trying to sum the electric field, I just have one kind of electric field going out there, so I don't really need the summation part. I can just write E. The area we just came up with would be 4 pi r squared. And then the cool part is the little area here would be, its direction would be straight up, and so is the electric field, it's straight up, so they are actually, it would be 0 degrees, so the cosine of 0 degrees is 1. We don't have to worry about this. It's just going to be 1, and it's going to be equal to the charge enclosed divided by epsilon 0. So here's the cool part, that if you are outside of the shell, then, so for part A, if you're outside the shell, then this little r that they kind of have written is greater than big R. And you could actually solve this, that your electric field would equal, I'll divide this 4 pi r squared over the other side, it would be Q divided by 4 pi, I'm going to actually put the epsilon 0 next, and then r squared. Why is that important? Because this is actually equivalent to k times q over r squared, because k, in my notes, is actually equal to 1 over 4 pi epsilon 0. So it's kind of a way of showing that if you have some charge and you're far enough away from it, a spherical charge, or it could be a point charge, that it would actually have an electric field equal to kq over r squared. And we just write it in terms of epsilon 0 instead. So this is how we would find it. They would just have to tell us how far away. The farther away we got from it, the smaller the electric field, because the electric field and the radius, or the distance from the charge, are actually inversely related. So since they're inversely related, and actually an inverse squared relationship, that if you double the distance, you actually get 1/4 of the electric field. Okay, what about B? What about inside the shell? So if you are inside the shell, if you notice here, they have like this is a little radius R1. I'm going to actually change the color. This is a little R1. And your instinct is, hey, I'll just use the same equation and it's going to be the same. But it's kind of a trick, because you have E, you have your 4 pi R1 squared is going to equal, but it's going to equal to Q enclosed. Is there any charge enclosed inside of this thing? And there is not. All the charge is on the outside of it. So since there's no charge inside or enclosed by it, this would equal 0. And the only way this could equal 0 is the electric field would have to equal 0. So one of the things I put in my notes is that inside of a charged object, you actually have no electric field. And we prove this, or we support this idea, I shouldn't say prove, but we support this idea with Gauss's law. So this is a little bit, I'm going to do a problem for you that you're going to actually have some numbers to calculate. It will actually have a theta in there that you'll use, or a phi. Sorry, I'll have an angle in there that you'll use, but just kind of give it at the beginning of this. But Gauss's law is something new that we've never seen, and I just thought I'd throw it out, and then a little bit of the notes on that. Hope you enjoyed. Thanks for listening. Sorry I didn't get this into our Google Meet today.